I will be explaining insertion sort. So insertion sort is a relatively simple sorting algorithm. The first step is to look at the second element of the list, because any list that has one element is already considered sorted. So we look at the second element of the list and we compare it against everything to its left. If the second element is less than the elements to its left, we have sorting to do. If not, we kind of just leave it as is. So in this case, 2 is our second element and 3 is our first element. 2 is less than 3, so we store 2 as a key variable, and we copy 3 over to where 2 originally was. And now we're comparing it against the first element of the list. So instead of doing anything else, we substitute 2 in for the first element of the list. Now we know that these first 2 elements are sorted. Now we keep doing that throughout the rest of the array. So now now the value we're looking at is 4. 4 is greater than 3, so that means because this is already sorted in least to great, 3 is the biggest element of the sorted array. And because 4 is greater than 3, it means everything through 4 is already sorted. Next, we look at the fourth element of the list, which is 1. We see 1 is less than 4, so we store 1 as the key value. We shift 4 over, and then we keep comparing. So 1 is less than 3, so we shift 3 over and keep comparing. And 2 is greater than 1, so we shift 2 over. And again, we've hit the beginning of the array, so we substitute the first value of the array with the key. And now we know that everything through 4 is sorted. Again, this is an instance where the value we're looking at is greater than the last value of the sorted array, and we know this is already sorted from least to greatest, so we don't do anything here, and we now know that this is sorted. And finally, our last value, 5. 5 is less than 10, so we store 5 as a key value, and we shift 10 over, we copy 10 over, and now we're comparing 5 to 4. 5 is greater than 4, so rather than copying 4 over, we are going to substitute 5 in, and that's the end of that sort. And now, when you look at it, we should have a fully sorted array, 1, 2, 3, 4, 5, 10, from least to greatest. So this is the algorithm for an insertion sort. First, we have our header. It's going to intake an array. For now, we're calling it n. So the first thing you want to do is make sure that you're traversing the entire, well, not the entire array, the array starting at the first index. So we're going to say for I equals 1 until I is greater than the length of n minus 1. You'll see later we're indexing n by the value of I, which is why we're not saying n of 1 until the end of the array. So for I equals 1 until I is greater than the length of n minus 1, we are going to introduce a new variable j, which is going to be set equal to I. And j is going to hold the value to the right of the number we're comparing the key to, which will make more sense in a second. And then the key is going to be set equal to n at element I. So the value n is holding it at I. So that's why, again, we're using our I value in our for loop to traverse the array by indexing it down here for the key variable. So now we're going to have an if statement. So we're going to say if j, which as a reminder, j is the value to, or is the variable of the location of the value to the right of the value of the key. So if j is greater than 0 and key value and saying, okay, is it less than whatever is to its left? In that case, we're going to have to change it around. So we're going to say, if j is greater than 0 and key is less than the value of n at j minus 1, we are going to set nj equal to nj minus 1, and we are going to subtract the value of j by 1. So this is going to make sure that we're moving further to the left in our array and continue to compare the key value to elements further left and further left until we hit j equals 0. And at that point, all you have left to do is set the value of nj equal to the key. So this is saying, if j ends up equaling 0, kind of like how we did with the example, if we reach the beginning of the array, the first element of the array is set equal to the key. Otherwise, this condition is going to test false first, and the element to the left of the key is going to be greater than it, to the right of the key is going to be greater than it, which is what we want. And so then, at that point, we would set the value j n at index j equal to key. So this is the time complexity for insertion sort. For the worst case of insertion sort, that would be if every variable to the left, or every element to the left of every element in the array at the beginning was greater than the element to its right. So that means the array might look like something like 5, 4, 3, 2, 1. And this is the worst case scenario because that means we're going to have to perform the maximum amount of swaps per element. So if we start at the second element of the list, so that means we swap at most once. If we start at the third element of the list, we swap at most twice. So that's going to give us something like 1 plus 2 plus 3 plus all the way through n minus 1. And that gives us an equation that is n times the value of n minus 1. So we factor in the n, which gives us n squared minus n, but because it's time complexity, we're only focusing on the higher degree, which is n squared. So our time complexity for the worst case scenario is O of n squared, or O n squared. For our expected time complexity, our expectation is that 50% of the values to the left are going to be greater than, and 50% of the values are going to be less than. So that is essentially our worst case divided by 2. Now, that 1/2, so it's essentially n squared times 1/2, and that 1/2 is a constant. And again, because it's time complexity, we're not worried about the constants. So again, our expected case is n squared. Our best case is when the list is already sorted, and that means we don't have to perform any swaps. So that would be something like 1, 2, 3, 4, 5. And that is, we just have to traverse the entire array, but we don't have to worry about making any swaps along the way, which means our time complexity is O(n), or just the length of the array.
I will be explaining selection sort. So if we take the array A here, selection sort basically finds the smallest in the array and swaps it into place until we have a sorted array. So in array A, we take the first element, and that will be our comparison point, and we go through the rest of the array, and we find the smallest element. So in the rest of the array, 2 here is the smallest element. So in the next iteration, we would switch 2 and 5. So we would have 2, 3, 9, 4, and 5. So now, our next comparison point would be 3, and we compare that to the rest of the array, and we see the minimum value would still be 3. So the next iteration would still look the same. It would be 2, 3, 9, 4, 5. Now, our next comparison point would be 9, and we're looking to swap with the smallest value. So in the rest of the array, our smallest value is 4. So the next iteration is 2, 3, 4, 9, 5. And our next comparison point is 9, and among these two, the smallest value is 5. So our last iteration would be 2, 3, 4, 5, 9. And there's our sorted. Now let's look at the pseudocode for selection sort. So as we saw earlier, we need a for loop to go through the entire array. So this would go through the entire array, and then we need a placeholder for the minimum value. So we could do that and set that equal to I. And then because we're comparing one value to the rest of the array, we need a nested for loop. That would go to the end of the array as well. And then inside this for loop, we're comparing the minimum value to, we're comparing the comparison value and the swap value. So we're going to need an if statement that compares whatever's at j, so that's the next element in the array, to the minimum value. And if it is indeed smaller, we set minimum equal to j. And then, so that continues until we find the smallest value in the array to compare to swap it with. And outside of this for loop, we would swap the element at I with the element at min. And that's how you would do a selection sort. Now let's look at the runtime for selection sort. So all of our cases, best, expected, and worst, are all n squared because we're going through n comparisons for n amount of items. So if we look at the pseudocode we wrote earlier, our first for loop goes through n elements, and our nested for loop also goes through about n elements. So we're going through n elements n amount of times, hence n squared.
I'll be covering merge sort. So merge sort is an algorithm that uses the divide and conquer strategy. And how it works is that it takes an input array of n elements and recursively divides that array in half until it gets to a subarray of one element, and then it sorts and merges each of those subarrays together to form one sorted array. And it consists of two main parts. One is the main function, which is the merge sort function, and the second part is the merge helper function. So now I'll be going through the pseudocode for merge sort. So first we'll write the main merge sort algorithm. Merge sort, and it takes as input an array that we're going to sort, and we'll call that R, and then it also takes as input low and high, L and H, and that is basically, low represents the index of the first element in the array, and high represents the element that's the last element in the array, the index of the last element in the array. So now we're going to cover the base case, and the base case is when the input array is of size 1. And so that means it only has one element in the array, which is already considered sorted. So the way we check that is we just do an if statement, and we check if the length of the array R is equal to 1. And if it is, we just return that array. Next, if the length of the array is greater than 1, then we're going to find the middle value in the array. So we're going to just do low plus high divided by 2. And so in this example, low would be 0, high is 7, and so low plus high would be 0 plus 7, which is 7, divided by 2, with integer division, that's 3. So mid would be at index 3. Then we do two recursive calls to merge sort. The first one is on the left half of the array, and so we're going to assign that to a variable called left. Merge sort. So we're going to call this on the array from low to mid, And then we're going to do the same thing for the right half of the array. Merge sort from in the array from mid plus 1 to high. And finally, we're going to call merge, the helper function, and we're going to merge together the left and the right halves of the array. So left, right, and we would just return that. And that's the merge sort function. So now we'll go through the pseudocode for the merge helper function. So merge takes as input the left and the right arrays that we had talked about in the merge sort function. So for consistency, I'm also going to call them left and right here. Now we're first going to define some variables. So we're going to have the result array, which is going to be the array that we're going to put all of the elements in left and right into and sort them. And then we also have two variables, I and j, which we're going to initialize to 0. And these are going to be the running index variables, index variables for left and right respectively. So then we're going to have a while loop, and this goes through the left and the right arrays at the same time and puts in their elements into the result array in a way so that all the elements in the result are sorted. So we're going to have, while I is less than the length of left, and j is less than the length of right, we're going to have an if statement that checks whether the element in left or right is smaller. So if the element at index I in left is smaller than the element at index j in right, then we would add that to the end of the result array. Result.append, and then left at I. Otherwise, the element right at j would be the smaller one, or they would be equal, in which case it doesn't matter which one you put first. And so then we would append the element right at j. And each time you do that, you have to increment the I and j variables. So you would have I++, and in this case you would have a j++. Next, when this while loop is done, that means that we've either gone through all of the left array's elements, or we've gone through all of the elements in the right array. And so that means that we might not have gone through all of the elements in the array, in the other array. And so for that, we're going to have 2 additional while loops to go through the array that has elements that we haven't seen yet. So this first while loop is going to be for if there's elements in the left array that we haven't seen yet. So while I is less than left.length, we're going to add the rest of left's elements into result. we'll increment the I variable. And otherwise, if it's the right array that still has elements we haven't seen, we're going to have a while loop for that. So while j is less than right dot length, we're going to add the rest of the elements to the right into result. And after that, we're just going to return the result array. And that's the end of the merge function. Merge sort has a runtime of O of n log n for both best, worst, and also expected. And this is because merge sort first recursively divides the input array of n elements in half, and so that's where the log n comes from. And then it also sorts and merges all of these subarrays, and that takes n comparisons and therefore n time. And so in total you would get n log n.
Hello, today we will be discussing quicksort. So the basic idea behind quicksort is that it recursively partitions an array around a pivot element, so that all of the elements that are to the left of that pivot element is going to be less than that value, and then all the elements to the right of the element is going to be greater than that value. In this way, we know that the pivot element is always in that right place. Okay, so we're going to start with our quicksort function. It's going to take as input our array, we're going to call it A, and then it also takes the leftmost and the rightmost element. That's just so we could see like how large the array is. And so because this is a recursive function, we need a base case. The base case in this case is when the array has size 0 or 1, and that's when the leftmost and the rightmost element, the position of those are the same. So we're going to have if L is greater than or equal to R, then we're going to return our finished array. So if this is not the case, we're going to move on to our next step, which is to choose a pivot. So there are multiple different ways you can choose a pivot. It could be the minimum value, the maximum value, the first element in the array, or the last element, or the median. It doesn't matter what it is right now, but it will matter later. So I'm just going to put our pivot in a variable called p and call a function choosepivot, which will take as input the array and the leftmost and rightmost element. So now that we've chosen our pivot and the position of it is in P, we want to make sure we know where the pivot is. So for that, we're going to swap the pivot's position and the first element's position. So that will be swap and this is so we can know exactly where the pivot is when we move on to our next step, which is partitioning. So we're going to put our partition value in A, and we're going to call our partition function. And that's going to take as input our array and the leftmost and rightmost element. Okay, so now we're going to talk about our partition function. So it takes as input the array A, which we had here, and the left and the rightmost elements. And so the first thing we want to do is have our pivot function, or our pivot value. So we know from here that we have our pivot in our first element of the array. So we can just get that value and put it in P. So now we have to partition it. We want to arrange the elements so that it looks sort of like this. So the first element is the pivot, and then we have all the values that are less than p, all the values that are greater than p, and then all the unpartitioned values beyond. So we want to have pointers to figure out where the boundaries of these are. We don't need a pointer here because we already know that pivot is in the first position. So we want something here to differentiate the less than p and the greater than p. So we're going to have I point to the first value that is greater than p, and then j point to the first value outside of this greater than p, so the first that is unpartitioned. So we're going to initialize I as L plus 1 because it starts off at the first element after the pivot, and then we're going to have a for loop that starts from j equals L plus 1 and goes to r, which is the last element in our array. And so inside of this, I'm going to be working with this example function. So let's say that the 3 is our pivot right now. So I and j are both on 8 right now. So what we want to do is go through all the elements. If it's greater than p, we don't really need to do anything because it's already on that side. But if it's less than p, we want to move it to the other side of the I. So we're going to have an if statement here. So if a j is less than p, we want to switch it with an element on this side and then increment I. So we're going to do swap aj and ai here. And then we're going to increment I because that will be another element in the less than p section. So I plus plus. And then we're going to do that until we've gone through each element in the array. So if we're going to use this array as an example, we're going to look at the 8 first. The 8 is greater than 3, so we don't really need to do something. So the j moves on to the next element. So the j is now at 2. 2, however, is less than 3, so we're going to need to do a swap here. So we're going to swap the 2 and the 8. The 2 is going to go here, 8 is going to go there. And then we're going to increment I. So I is now there. So now you can see this is where the less than p section is, and then this is our greater than p, and then all of this is like unpartitioned. So then we're going to move on. The j is going to move to the 5, and then 5 is greater than 3, so it doesn't really do anything. Then we have j at 1. 1 is less than 3, so we're going to do our swap here. We're going to swap it with this 8. And so now this is where our less than p is. We're going to increment the I, so I is right there. And this is where our partitioned greater than p is. And this is our unpartitioned. And then it's going to go through the rest of the array. These are all greater than p, so it won't do anything else. So this is our partition right there. So after it goes through all of this, and it has like these basic categories right here, we need to make sure that the pivot is in its right spot. So the 3 is supposed to go between the less than p and the greater than p section. So what we're going to do after this for loop, we want to swap the element in the first position of the array, and then this one right here, which is I minus 1. So a L, and then a I minus 1. And then, so that's my desired right here. 1 is here, 3 is there, 3 is still a pivot. Okay, so now this is like fully partitioned. So it now returns the new position of P, which would be at I minus 1. So that's the end of this partition function. This will return back here. So A is now the position of our pivot. And so now we have one recursion of this array, but the side on the left right here, the less than p side, this is unsorted. it looks sorted right now, but the program doesn't know that it's sorted. And then this half of the array is also unsorted, so we need to call quicksort on the left hand side and the right hand side of this array. So we're going to do quicksort. It's the same array, A, and then it's going to go from the left hand side to this right here, which is A minus 1. And then we're going to do quicksort A, and then let's go from A plus 1 to the end of the array, which is R. And that's it for quicksort. So now we're going to talk about the complexity of quicksort. So because quicksort is a divide and conquer algorithm, the complexity of the worst case, best case depends on what you choose as the pivot. So the best case is O n log n, and this is when the pivot is in the middle of the array or the median value. So if we're going to have an array like this, it would partition all the elements, and then we would break it into two arrays that look kind of like this. And then this would break further, and it would be smaller and smaller arrays. But each time, it's dividing it into approximately half. So the work done at each element would be n here, because the partition function looks through each element in the array, so it would be n amount of work in this level. And then here would be n divided by 2 amount of work here, approximately n divided by 2 amount of work here. So in total, it'd be n here, and then it'd also be n in all the other ones. So in each of these levels, there's n amount of work happening, and then the number of levels would be log n, because if you're constantly dividing something by 2, the number of times it takes to get to 1 would be log base 2n. So if we have n amount of work each level and n or at log n levels, we would end up having n times log base 2n. And then because this is, we're taking the big O of it, the base doesn't matter, and that's how we get O n log n. So now, if we're talking about the worst case in this is when you're always choosing the minimum value of the array. So that is, if we have an array of this size, we have our pivot here, and all the other values are greater than that pivot. So when it breaks off, there's nothing to break on this side. It'll only just break breaking here. So then our next iteration will look like that. And then it'll keep cutting off just one element, like that, until we have like one element. So now the work done at each of these elements, so the first one would be n, because it would look through all of the elements in the array. This would be n minus 1, because it only gets rid of the pivot. It still looks through every other element in the array, and then the next would be n minus 2, all the way until we have 1. So now if we add up all these values at each level, we get over 2. And then when we take the big O of that, it ends up being n squared. And then for expected case, it would basically be picking any like random pivot in the array. So it could break up this array in any different ways. It could be like 25% on one side, 75% on the other side. It could be 40, 60. It could be any kind of ratio. But the amount of work would still be n at each level approximately. It would just be the height of the tree, we could call it, that changes. So really the only difference that it's making is the base here. And the base doesn't matter when we're doing big O. So it would still be O n log n for the expected case. And that's all there is for quicksort.